Welcome to qnawire.
So we have the mean lifetime of the muon in its own reference frame, which is 2.2 microseconds. With this time, we also take into consideration the greatest speed that the particle could have, which would be the speed of light. That's the fastest anything can travel. So in its own reference frame, the muon can travel a distance of, if we just simply multiply use the formula distance equals speed times time, we would have the speed of light times this lifetime. The greatest distance it could cover in that time would then be, if we multiply these together, we get zero point 0.6, or basically 660 meters, which converts to 0.66 kilometers. So it couldn't get very far. The atmosphere is 10 kilometers thick, so with this by itself, the muon would not make it to the atmosphere. So we definitely have to think about relativity. So the next thing we think about is time dilation in relativity. So we can relate the time to an observer on the Earth to the time of the muon, or basically the lifetime of the muon. So if we write this equation, which relates the two times, and we have a velocity of the muon of 0.999 times the speed of light, then we go ahead and we make a calculation. We put in for delta T naught the mean lifetime of the muon, and of course we put in the velocity. Then we get 4.92 times 10 to the minus 5 seconds. That's 49.2 microseconds, but we'll simply leave it in units of seconds. Now we can go and calculate the distance that it can travel. So here what we do is, this is relative to somebody on the Earth. We say, all right, the distance is equal to the speed, 0.999 c, times the time relative to an observer on the Earth. And this distance calculation gives us 14,745 meters. So we see we see a substantial difference in the two calculations. This translates into 14.7 kilometers. So if the atmosphere is 10 kilometers thick, but the muon can now travel 14.7 kilometers, then it can reach the ground. So we see that because of time dilation, the muon can actually reach the ground. So the next thing we want to think about is from the perspective of the muon. They do travel very fast. We saw that, a typical speed might be 0.999 times the speed of light. Well, from the muon's perspective, that means that the thickness of the atmosphere is going to be length contracted. So we use the length contraction equation and we apply that to the thickness of the atmosphere. So I simply write L for the length is equal to, the length in this case being the thickness of the atmosphere that the muon sees, is going to be 10 kilometers times the square root of 1 minus 0.999 squared. Because remember, in the atmosphere's frame of reference, it's 10 kilometers thick. But in the muon's frame of reference, it's going to be 10 kilometers times the square root of 1 minus 0.999 squared, since that's the length contraction equation. So we end up, the muon ends up seeing that the atmosphere is 0.447 kilometers thick, or simply 0.45 if you want to round it. So 0.45 kilometers, and that's less than the distance that the muon can travel in its own frame of reference, given its lifetime. So indeed, it is able to reach the ground because the atmosphere is length contracted.